How is it possible to see the hairs on a fly's leg or image objects the size of a single virus? Before the invention of the scanning electron microscope, or SEM for short, the only practical option was to use a light microscope. However, imaging small features with this technique is very difficult. The narrow range of focus makes it complicated to see 3D detail of a sample. Chemical treatments must be used to distinguish different materials, making identification complex. The maximum magnification, around 1,000 times, and shallow depth of focus makes it very hard to see the details on this fly. Luckily, the scanning electron microscope is an alternative to light microscopy, which is much better in these areas. In the electron microscope, electrons behave as waves. These waves have much shorter wavelength than visible light, by 100,000 times. This allows us to see an extremely high resolution into a world that was previously hidden to us, with features as small as 1 nanometer. This is up to 200 times smaller than optical microscopes, or the same difference between the Empire State Building and a desk chair. Let's look closer at the SEM to understand how it works differently to an optical microscope. You may be familiar with the usual setup of a microscope, which has a light source which interacts with the sample and is then focused to create the image. In the SEM, the light source is an electron gun which fires electrons at high speed onto the sample. This beam is focused by electromagnetic lenses to create a narrow beam which hits the sample rather than illuminating the whole area. When the beam hits the sample, 2 primary signals are created. Electrons can be removed from atoms in the sample, releasing them to the detector, giving strong signal variation with surface topography, or electrons from the beam can be reflected by the sample, which give an indication of the elements present. X-rays are also released, which give further information about the atomic composition. Detectors measure the signals produced by the beam hitting the sample to give the brightness of a single pixel on the image. As the beam changes position, the image is built up pixel by pixel. This means that instead of many detectors taking an image instantaneously, there's only one detector and the image is taken over a period of time, often minutes. With this setup, the magnification of the image is not changed by adjusting lenses, but by changing the area that the electron beam is scanned over, allowing the SEM to create images over a very large range of length scales. Let's see how this works in practice when imaging a fly. We first mount the fly onto the holder using conductive paint. Next, a thin layer of gold is deposited onto the fly. This is to make the surface conductive, as otherwise it will become charged by the electron beam, cause the image to be distorted.
We prepared our samples by coating them with gold, and now what we're going to do is we're going to mount them onto the sample holder and then put them in the SEM, and then we can see what they look like.
Now all we need to do is place the holder into the SEM and evacuate the chamber. We can now move the view around and take images freely. Scientists can understand a lot about the materials they are studying with SEM. This has made it an indispensable tool for many fields of work, including commercial, scientific, industrial and medical. 3D images of specimens at high resolution, structure and chemical composition can all be seen. SEM has contributed enormously to research such as deepening scientists' knowledge in developing semiconductors and microchips due to its easy interpretation and resolution.